Welcome back and thank you for joining. We'll continue with the lesson U3L1 where we are exploring the first derivative and learning how to use it to describe the increasing or decreasing behavior of a function as well as determining the min and maximum points, which are also called the turning points or the extrema or the critical points. So mainly we looked at examples of polynomial functions, and to find the derivative of polynomial functions, you know that we use what we call the power rule of differentiation, which means that we mainly use the formula x to the power of n, though the derivative of it would be equal to n times x to the power of n minus 1. So this time we are going to take a look at a slightly different equation. So we are still using the power rule to differentiate the function, but this is not a polynomial function. And the way we know it is because the power is 2 over 3, so it's not a natural number. So we're going to start off by differentiating this function. So obviously it's the same thing we're doing in here, so we're trying to find all the critical numbers and classify them as min, max, or neither. So the derivative of f of x or f prime x would be equal to, again based on the power rule, the derivative of x to the power of n is nx to the n minus 1. So that means that we'll have 2 over 3. X plus 2 doesn't change for now. Then we subtract 1 from the power of 2 over 3, and we also have to look into the derivative of the inside because you see that we have a small little chain here. So the derivative of x plus 2 is equal to 1. So let's simplify this. So as you can see, we have 2 over 3, and the numerator has x plus 2 also to the power of 2 over 3 minus 1, which is 2 over 3 minus 3 over 3, which makes negative 1 over 3. And you multiply by 1, nothing changes when we multiply by 1. And the next thing that we want to do is rewrite the derivative with positive exponents. The reason why is because in order to study the behavior of a function by using the first derivative, we need to study the sign of the derivative. And to study the sign of any expression, as you can see, derivative in itself is a function. We need to find the zero of it because the zeros will separate the positive from the negative values. So as you can see in here, in this case, we have a rational expression that represents our derivative, which means that to study the sign of it, we need to consider both the numerator and the denominator. Now, luckily, our numerator is a constant number, a constant positive number. So we're going to say that numerator is equal to 2, which is a positive constant number for any real number x, which means that the sign of the entire derivative will be dependent on the sign of the denominator. So let's write the denominator here. As you can see, the denominator has a variable x, and we're trying to find the zeros of it so that we know when this expression will be positive or negative. So divide both sides of this equation by number 3. So this is very straightforward. It doesn't need so many steps actually, but I'm just trying to show the steps so no one is lost in the process. So next we have to bring both sides of the equation to the power of 3 so that the exponents 1/3 and 3 will multiply to give exponent of 1. So now we have x plus 2 equals 0 to the power of 3 or 0. So that means x equals negative 2 will be the 0 of the denominator. Now we can say that we're ready to study the sign of this derivative. So since the derivative is simply a constant positive divided by 3, and then x plus 2 to the power of 1 over 3, we can study the sign of it entirely in one step because, again, as we said, is dependent only on the sign of the denominator. So here's the number line from negative to positive infinity, and here is the 0 of the denominator, or the only key value we have here. Now, at negative 2, the denominator will be equal to 0, which means that the derivative at negative 2 will be undefined. So to the left side of negative 2, so from negative infinity to negative 2, the x values substituted into the derivative will give this entire expression a negative sign. So we can find out or determine this by simply substituting an x value anywhere in this interval, or simply remember that if x plus 2 is a positive number, the third root will be positive. If x plus 2 is a negative number, the third root will be negative as well. So wherever x plus 2 is positive, this entire thing will be positive. So remember that x plus 2 has a positive slope, which means that it will be negative and then positive after the 0. Or you can simply substitute again the x values from each interval that is created by the critical point here in the domain. So since the derivative starts with a negative, it means that the function, the behavior of the function will be a decreasing behavior here. And when it's increasing, positive derivative will give or will make the graph of the function increase. So indicates that the graph of the function is going up and the function itself is increasing. Now exactly at x equals negative 2, the value of the derivative is undefined. So now the question is, what happens to the graph of this function? So what happens when the derivative is undefined? Would the function still be undefined just like the derivative? Or would we see something different or something special on the graph of this function? So remember that the derivative of a function may not exist for two reasons. Reason number one is if f of x is undefined, then the derivative will always follow and f prime of x will also be undefined at that point. But sometimes what happens, and we've seen examples in class, f of x may be defined throughout the domain, but then the derivative may be undefined at some specific point. So it doesn't have to be undefined everywhere, obviously, but at some specific point, it may be undefined. So the reason why is because the derivative of a function, remember, describes the slope of the tangent drawn on the graph of a function. So obviously, if the function is undefined at a point, so if it has a hole or a break, then we cannot draw a tangent, and thus we cannot measure the slope of the tangent. So that's the reason why we say that if a function is undefined, derivative is undefined. Now, the second case scenario is a function may be defined at a point, but then just the derivative is undefined. And we have seen the graphs of functions that appear to increase extremely fast at some point, but they're still continuous at that point. And what happens is that when you draw the tangent will be a vertical line, and vertical lines have undefined values of slope. So if the slope is undefined, that means that the derivative is undefined. So there are two different cases. So let's examine the domain of the given function. So when we look at x plus 2 to the power of 2 over 3, and this is the way I like to see it, that's how I like to determine the domain of some strange, unknown, never seen before type of functions. So I imagine if I substituted x, let's say, for example, by a positive number, let's say 5 plus 2 to the 5 plus 2 is 7. Bring it to the power of 2 over 3, we're going to get a positive answer. If x happens to be 0, 0 plus 2, that will give a positive 2. To the power of 2 over 3 will give some positive answer. So the value of the function exists. If x equals some negative number, let's say, for example, negative 5. Negative 5 plus 2 will be negative 3. Bring it to the power of 2 over 3, which is basically the third root of negative 3, brought to the power of 2. That would be simply the third root of number 9. And the third root of number 9, which is a positive number, but even if the number inside the third root were negative, the value of it exists. So what that tells us about the graph, the equation of this function, is that the domain of the function itself is any real number x. So what is special about this derivative then? So what is happening? So the fact that the function is defined at f of x, at x equals -2. So f of x is defined. And if we actually want to figure out the value of it, we can substitute x by -2 in here. So we have the square root of -2 plus, the third root actually, of -2 plus 2 squared would be the third root of number 0. Okay, that was a little harsh here. So the third root of 0 is 0. So we're going to say that the function itself has no restrictions, but the derivative has a restriction at -2. So now we're thinking, what would be the shape of the graph then? So again, as we have mentioned in the past, there are cases where the graph of a function may be defined at a point, but still the derivative doesn't exist. So some of the graphs that we have seen that may be continuous, right, but have unmeasurable slope of a tangent are, say, absolute values, so because the rate of change or the derivative will be different at different sides of the critical point here, or the slope of the tangent is vertical, or when we see CUSPs, right, so where the value of the slope of the tangent will be undefined as well. So we are trying to figure out, in this case, what the shape of the graph is going to be, and what we're going to do is look at the graph on Desmos. Oops. So what we have here is y equals, and we had x minus 2 to the power of 2 over 3, we said, right? So 2 over 3. So let's take a look at this graph. I'm going to change up the scale in here. So as you can see, what we have here is a small little cusp at x equals, actually we had a plus in here, so let's fix that. So it was plus, so the cusp will appear at the critical point at -2. So we are going to say that at the restricted values, or at x equals -2, the graph will show a cusp. So in conclusion,